Good afternoon, ladies and gentlemen, and welcome to Neutech Park. My name is Andrea Valenari, and I'm a subject matter expert, automotive and mobility. It's a pleasure for me to have you here, and I will also happy to be the host for this event, Sustainable Material Plastic Transition. This event is a part of the Impact project financed by EU within FASER program. Our objective to Neutech Park is to boost research and development to create innovative business and sustainable impact to our region. NOI means nature of innovations. Therefore, hosting an event like this is perfectly to our DNA and help us promoting change in science, technology, and society. So about the event today, we have opportunity and insight. Today, we have a great audience and speaker thanks to company representative of the automotive field, sporting goods, agricultural machine, building and construction, plastic raw material producer, startup, research institute, and university. So all the ingredients are today present here, and I hope this allows something happen. So about some insight, we know that sometimes plastic waste could be also a resource for sustainability plastics. And so there are also some growth drivers. Bioplastic is a business which will be increased between 2024 and 2030 with about growing rate about 8%. Due also for the stringent government regulations. But there are also some challenges. There are also still problems regarding the production cost of biopolymer and also limited resources availability. But before going into the details of the programs, it is also our use to give our warm welcome from our director. So we have here today our Director for Tech Transfer and Innovation Management, Vincent Morgois.
Yes, thank you, Andrea. So I was told we do everything on English today, so I will speak English, but benvenuto e welkom aan allen trotzdem. Welcome, especially with the logistical difficulties. So as you know, we have also a very high-level political visit here. So Minister Pantedosi is here, Minister of Internal Affairs, linked with an event related to the safety and security on the workplace. And they have chosen Neutech Park as a place to hold that event. So it's good that the place is also attractive. We also had Meloni here. I don't know if you heard March, April also President Meloni was here. And unfortunately it has a big impact on our logistics that sometimes we don't have under control. So normally we do our events in the seminar area. We could not do any event in the seminar area, so we have to try and find an alternative solution. And it's already since 3 weeks that they are checking the location and make sure that everything is secure. So thank you for the effort of coming here. I'm conscious that it was not easy to be here. Approximately 100 people at least subscribed. Could be that we are approximately 100. So thank you. Yeah, so sustainability as a whole, but especially sustainability related to material is a big topic, as you all know. I think it's not an option anymore, it's a necessity. It's not an easy necessity, so we have always more and more legislations and laws that push everybody along the entire supply chain to be more sustainable. And on the other side, we have also the demand of a lot of customers who meanwhile expect also from the product to be more sustainable today or tomorrow compared to yesterday. The event shows also our commitment related to that topic. So as Andrea already said, sustainability is in the name, nature of innovation. It's also one of the pillars of our strategy, sustainability, next to being also a lot of expertise and pioneering. Sustainability is core, and what we always pay attention to also in everything that we do in innovation management and new business models is that we not only look to the environmental sustainability, but also the economical sustainability. So also the solution should be able to withstand time and be successful in the market, and that companies and startups maybe also can survive also long term. What makes it also difficult, I think, sustainability is that it's always more and more a common effort. It's very difficult for single companies to do things alone because at the end you need your supply chain, you need your suppliers, you need your equipment suppliers, maybe also the logistics to think the whole with you. And that is also why places like Neutech Park, where we foster collaboration on different fields, be it startup, company, research is very important. And also the legislators is also very important. Sometimes we have also local politicians or Italian or a local who are also deciding on the laws. And that is also important that we have them also included in the whole loop so that we all together do it in a syntony instead of working against each other. So I'm very glad also that we have a list of interesting companies from different fields, some thought leaders, I would say, some innovative companies. We have research, so I think it will be a very interesting day. What we see also from everything that we do is that transversality is very important. So that sometimes the solution is not necessarily in the sector or area that you are working for or working in. I take an example from automotive. I also come from automotive. You tend to look only in automotive where the solution is, and sometimes you can find a solution, or the solution is already in another sector and industry that you can adapt, at least for your needs. So that is why also that heterogeneous group, I would say, of people, different companies, backgrounds, is normally also very interesting. So we will see some in the program some very interesting new insights related to high post-consumer and post-industrial content. And we will also see some interesting breakthroughs related to bio-based and biodegradable materials and the usage of those. One of the most important things I would say is that the important thing is the know-how that you will receive and that you can absorb. But maybe as important is also to learn to know each other and to find ways to interact and eventually also work together in projects that we are, of course, very well and very glad present also to help you to kick them off. Yeah, that is approximately what I wanted to say. And before we start with the program, I would want to hand over to Mirko Brusco. He's the representative of the group Chemistry and Plastics of the South Tyrolean Entrepreneurs Association, and he will give also an introduction. Mirko.
Thank you, Vincent. Thank you, Andrea. It was given the instruction to do in Italian language. Some introduction word in English. Thank you for having me here, and for me is, at the moment, sono rappresentante dell'industria di Confindustria Alto Adige per il gruppo Plastiche e Chimica, quindi è un piacere, grazie dell'invito, grazie anche dell'organizzazione perché sicuramente non è stato facile, è veramente bello vedere questa grossa partecipazione in un settore che conosciamo, quello delle plastiche in evoluzione. Principalmente parliamo di due filoni, uno che riguarda il riciclaggio e conosciamo che c'è il post-industrial e il post-consumer. Nel post-consumer abbiamo un'ulteriore sfida che è quella di separare i materiali piuttosto che di rendere riutilizzabili, quindi parliamo ancora di costi che al momento il mercato non è pronto ad affrontare, ed è per questo che siamo qui, per trovare delle soluzioni innovative insieme o tecnologiche per far sì che questi materiali possano diventare più competitivi. L'altro filone è quello nell'ambito dei materiali biosostenibili, da risorse naturali. Anche questo al momento, rispetto a quello che era stato detto qualche tempo fa, non sta prendendo così piede. Io conosco un po' meglio il settore automotive e quindi è molto importante oggi, mi fa piacere essere qui per ricevere i vostri preziosi input, esperienze che state avendo, per poter insieme aumentare questa capacità e questo mindset che abbiamo bisogno per appunto affrontare l'aspetto competitivo del mercato, ma abbiamo anche una grossa responsabilità per quanto riguarda la salvaguardia dell'impatto ambientale. Quindi è meglio dare la parola a voi esperti del settore, imprese, mondo accademico, ricerca, e auguro a tutti una proficua giornata di lavoro. Grazie.
Grazie Mirko. Thank you, Mirko. So, let's kick off this afternoon. Usually we try also first obtain a reasonable overview before starting and also give some motivations. And this event makes no exception about that. So I have to say really welcome to Eligio Martini, owner and president of MAIP and BioOn, strongly focused on green polymer. He started working on plastic just before 1980s, so he has really an impressive experience about plastics, and winning also several bioplastic awards and innovation. And in 2022, both patent and processes of BioOn produces sustainable bioplastics. So, Eligio, thank you to be here. The stage is yours.
Thank you, Andrea, for the invitation. I hope that we can, it doesn't work, maybe. Okay. Okay, today I speak about plastic and the future of the plastic a little bit. When plastic was born, it is seen as a democratic and ecological revolution. Why? Because plastic primarily served to replace natural material, for instance, to replace ivory, that was strongly used for the production of billiard balls. But also, it was used to produce other components that normally were used only by the richest people. And plastic became very democratic because any kind of people could have a special garment, have a special component in his daily life. At a certain moment, plastic became the fourth kingdom of the nature, was an unbelievable material, the material of 1,000 possible applications. So in that period, plastic was a miracle, not as in nowadays. But plastic is really, in my opinion, a fantastic material. I am strongly convinced that plastic is still one of the most important inventions of mankind. It's really important. Plastic changed our life completely. So we have to see that in any daily business, we find a lot of application of plastic. But we have a problem with plastic. One of the most important problems is the packaging, because about 40% of the total production of the plastic is made for packaging. Imagine that we produce, in our current period, about 450 million tons of plastic every year. And 40% of this plastic is for packaging. That means about 200 million tons per year. And we have a problem. We have a problem because packaging means also a lot of littering. Of course, we can recycle plastic, but Europe and Italy especially is very advanced in the recycling system. But for instance, in US, only 9%, maximum 10% is recycled. The rest is going to landfill, creating a pollution in a very huge area. Which is the problem of plastic? The durability. One of the most important advantages of plastic is that it's not easily destroyed. It's a durable material. This is a big advantage. It's not like metal that can be corrosed and our material. But this advantage is also the problem at the end of the life. We have a lot of problems, I repeat, with the end of the life. So every day you have something against plastic. Plastic is not able to degrade. When sent to landfill, it creates a lot of pollution, and so on and so on. And then there is also the man. The man sometimes is an idiot because many people are able to throw away plastic component. Why? So you find plastic littering on the beach, on the sea, everywhere. And this is really a problem, the littering. But you have to imagine one point that is very important. If we decide to replace plastic with another material, in any case, we will do some hostile act against the nature. Because only to give you an example, the CO2 emission will become 2.7 times more. It's an official number. So plastic is still an ecological material. But of course, we can forget what we can see every day. This is some slide, some picture in the world. Plastic pollution everywhere. Mostly in the sea, on the marine environment. This is the real situation. We see something. What we see, maybe everybody knows the problem of the plastic island, the plastic gears. But you have to imagine that the plastic that you see, the island that you see, an island is more or less similar as extension to France. Another island similar to Greenland, and so on, is only 1% of the plastic on the marine. 1%. More, there is a 4% on the beaches. But what is unbelievable, but is the reality, 94% is at the depth of the sea or in the ocean itself. I have not put a slide here, but imagine that some researchers of Newcastle University discovered last year a new type of shrimps, a new type, never discovered before. Well, discovered at a depth of 6,000 meters. The shrimps, a new shrimps, was called Eurysthenes plasticus. Why? Because in the stomach, the researcher found a piece of PET. The feedstock of the shrimp was PET. Imagine, at 6,000 meters. Why? Because we have a lot of microplastic. We have a primary, secondary microplastic. We have a microplastic and also nanoplastic that are more dangerous than microplastic. And all this type of material, sooner or later, are arriving to the humans. You see the new food chain. plastic, the bottle, shrimps or bird, and at the end we eat plastic, microplastic. Which is true, but not everything is true. Now, I give you, for instance, an idea about some fake news that are coming on microplastic. WWF, it is a famous world organization for the animals, said some years ago that each people is eating every week an amount of microplastic as a credit card. So 5 grams per week, terrible. Imagine everybody, you are eating 5 grams per week. And any kind of newspaper, magazine, reported this news. So for everybody, we are eating a credit card every week. But it's not true. It's not true. The American Chemistry Council made a real research on this. And this is demonstrated. And what they found, that is not 5 grams, what we are eating. It's not 5 grams. It's only 0.00004. So before we are eating a credit card, it will pass 10,000 years. So it was really a fake, completely. But nobody was saying that this was a fake. The official news is that we are eating a credit card. Why? Money. The reason is money. Newspapers are able to sell more if the news are negative, not positive. And also the ONG or ambientalist organization can receive money if the news are terrible, not if are positive. Say no to plastic, ocean is full of plastic, and so on. Do you want to see another fake news? Straw. It was reported by many magazines, Washington Post, National Geographic, Fox, everything, that in the US, we are using 500 million single-use plastic per day. 500 million, imagine the number. Terrible, terrible. So, which is the reaction? We have to avoid the use of plastic straw. But where come it from this news? Which has been the study behind this news? Now I give you the answer. A boy of 9 years old, a boy, he made a sentence per joke. He write 500 million, he could write 1 million, 500, 1,000 million. He wrote, everybody reported this number, and now become an official news. It's not true. It was a boy. And now we don't produce no longer plastic straw for a fake news. But I don't want to say that microplastic is not a problem. It's surely a problem. These are 2 different types of report. Both studies are saying that there are many different components that are producing microplastic. More or less, the first 2 dangerous components are the pneumatics, because there is vibration, It is rubber, but everybody is considering plastic. And washing textile. We are speaking about a lot of microplastic. Imagine that every year in the sea, anyway, are arriving about 12 million tons of plastic. Of this, about 1 million ton is primary microplastic. I mean intentionally added microplastic, primary. And one of the most terrible problem is the washing of polyester textile. The normal washing machine are not able to make a good filtration for this. So it's normal to say that it's better to use a natural material. For instance, like cotton. Cotton is natural, it's not like plastic. But we have always to give a complex view of everything. So the question could be, what is more friendly between cotton and polyester? I have to tell you one point more. What is the most important resource for our period? Water. Water. We need the water, and the ecosystem of water is collapsing. This year, I was in vacation in Uzbekistan, and personally, I saw what is happening in Aral Lake. This is the situation. There is no water. The biggest lake in the world now is without water. The boats are on the land, no water. Turkey was a country with a lot of water in the past. Now they are starting to need to find the water. And what is happening? A geopolitical war. Do you know where there is still some water? In Kurdistan. This is the real reason for which Turkey is trying to take a lot of land from Kurdistan for water, not for the petrol, for water. So water is precious. And I come back now to the question, polyester or cotton? To produce 1 kilo of polyester, you need 20 liters, 20 water liters. If you need to produce 1 kilo of cotton, you need 11,000 liters of water, 550 times. You need a lot of water. You are destroying the country if you take the water for producing cotton in a natural way. If you take a t-shirt, a cotton t-shirt, to produce one single t-shirt, you need 2,700 liters of water. So be careful to say that cotton is better than polyester. Another fake, Greenpeace, very famous. Greenpeace, to tell the truth, lost a lot of its credibility because of the founder of Greenpeace said, despite my best effort, the movement abandoned the science and logic somewhere in the past. Now, it's not scientific at all. They publish a book, Biodegradable Plastic on the Sea. In the book was written, bioplastic do not degrade in the marine water. Officially, Again, this is a fake news. It is not true. At least there is one material, one biopolymer that is able to degrade in the water. This material is called PHA. that is a possible solution for many problems from a biological point of view. This slide comes from plastic consultant. The question is, plastic, the way nature intended, piace? The answer is easy. Yes, because it's not a plastic. PHA is not a plastic. PHA is a natural material created by the nature to return to the nature. It's created by some microorganism. It's a revolutionary material, absolutely natural, as our skin, our hair, our DNA is a natural polymer. It's 100% bio-based because it is created by the nature. And unbelievable, can be transformed with all the technology of the plastic industry. It is transformed. You can mold, you can extrude, you can make rotomolding, you can do everything. But frankly speaking, we can consider this as a plastic. It is biodegradable in any ambient, in any environment. And this is written by something that is studied by Innova in Germany. But of course, we face microplastic in any kind. Also in agriculture, you see some part. But we can produce this part now in PHA. A PHA, if it falls down on the land, becomes a fertilizer. It don't become a microplastic. It becomes a fertilizer. So, plastic is not a devil. It's really a big invention, important invention of mankind. But check the news by a scientific approach. Not everything is true. PHA is an angel that could save a problem. Where is my conflict of interest? I am half devil and half angel. So interiorly, I have a big conflict of interest. But at the end, which is my dream? My dream is to combine nature and future. Thanks for your attention.
So, thanks so much, Eligio. So it was very interesting. But we have a little bit to speed up here. And I will also introduce the first keynote also presentation. After packaging and building and construction, automotive industry is the third biggest consumer of plastics. It is interesting to know the ongoing process in this sector from OEM's perspective. The keynote we will see is made from Gabriele Ciaccio from Stellantis. Thank you, Gabriele, to be here. And Gabriele is working as a responsible of the biomaterial laboratory and have around 20 years of experience in the automotive sector. So please, Gabriele.
Thank you. Good morning to everybody. So as you see, I will talk to you about sustainability in the automotive. Okay, this is my agenda. I will go through the introduction, talking you first of all about our targets that have obviously an influence on what I will explain you after. And first of all, I have to talk you about one of the main targets that we have, an internal target. We would like to decrease our CO2 emission with two main milestones, one in 2030, with a cut of 50% of our CO2 emissions, and another in 2038 when we would like to achieve a net zero, so zero CO2 emissions. And, okay, thank you. And so what is interesting in the graph that you see in the slide is that there is a dotted line. The dotted line is rated the path that we will have if we will only electrify our cars, okay? You can clearly see that it will be not enough to decrease our CO2 emission and to meet our targets. This means that we'll have to work not only on the electrification, but also on the material and the processes that are used to realize the components used in our vehicles. So this is the other main, I said before target, this is more a constraint. This is the draft or the end-of-life regulation. At the moment it's under discussion. But anyway, currently you can read on it that in the future, that will be probably 2041, 2042, we will have a target of the 25% of the plastic in our vehicle recycled and post-consumer recycled. And the 25% of this 25% should come from end of life. Okay, so it's a huge constraint. And associated to this, there is also the indication that it will be necessary to create a circular economy strategy. And I will come back on this later. And there is a list of parts that it will be necessary to dismount from the vehicles at the end of the life. This is also impacting because if you see in the list, there are, for example, the dashboards that are not so easy to be dismounted because are inside the vehicle compartment. So then, moving to the materials, I will start from the soft trims. And I will start from the polyvinyl chloride that is commonly used in the interior of the vehicles. As you can see in the picture, we can use it to make seat covers, to wrap the steering wheels, or for the gear. And you can see also the structure of this kind of material. We have the backing that is made usually of polyester. Then we have several layers of polyvinyl chloride and a coating that usually is a polyurethane. So it's an heterogeneous material. Then if you analyze also the CO2 emission of the PVC, the CO2 emission of the PVC are quite good because are as close to the polyester, are better than the polyurethane and really better compared to the leather. So, from this point of view, the PVC is a very good polymer. But there is a main constraint. If I will have to recyclate the material coming from the vehicle, PVC will be an issue because it's a pollutant for the other polymers, and also because, as I showed you before, the structure is not a monomaterial, not only PVC, but we have also polyester and polyurethane. And we can see this thing clearly looking also at this other slide that is related to the structure of the material used for the seat covers. In this case, we have 4 examples. The first one is related mainly to the fabrics, okay, structure. Then we have, again, the PVC structure for seat covers. Another structure using a polyurethane coating, a polyurethane skin, sorry, and the leather. In all the 4 cases, we have a polyurethane foam and a backing made of polyester. Also, in this case, we can see that the structure are very heterogeneous. If I will have to recycle this kind of material, it will be quite impossible. So the main way to reuse them will be burn them to obtain energy. What we can do? One possible approach on which not only us, but also our competitors are looking for is the monomaterial approach. So to substitute the layer, in the example here, the polyurethane layer that is between the 2 polyester layers with a non-woven polyester. In this way, we will have the aesthetic layer made of polyester, the layer in between that was before a polyurethane foam made of non-woven polyester, and the backing made again of polyester. This, from the point of view of the recyclability, is a very good option. From the point of view of a designer, is a constraint, because this will mean that the possibility to change and to propose to the customer something different. For example, if we are looking to Stellantis, we have 15 brands now. No, so to change from one brand on another, it will be really difficult. Okay, so I'm not convinced that at the end this will be the solution for everything, but for sure it will be something on which we will push to try to, at least for talking about the polyurethane, to try to avoid this mixture of materials. Something can be evaluated for the carpets. No? Also in this case, here we have not so much. We have also polyurethane, but the main material that is with the polyester is what I call it here the heavy layer, that is made of mineral fillers with PDM. Also in this case, we can move to a polyester non-woven. Here, the main constraint is not more the aesthetic, but so it's not an issue for the designer, but are the acoustic performances. So, jumping to the plastic world, first of all, I would like to say some word about our new approach with the creation of Stellantis. We defined some new codes to codify the plastic materials, and these codes are called GPC, the Global Plastic Callout, are a system of code. To this code are associated specific chemical, mechanical, physical properties, and to each of these codes we are associating several commercial materials. And in the example you can see, here we have a code associated to a thermoplastic olefin. You can see that in the code we have the indication of the filler, the quantity of the filler, and then some mechanical performances associated to that specific code. Moving to the standards that are associated to the codes, here you can see the three main families, the polyamide, the styrenics, and the polypropylene one. And in this part of the slide, you can see the table with the properties that I was saying before associated to the code that we saw before. So the chemical, physical, mechanical properties that we will have to fulfill to codify a commercial grade with the code that we saw before. And the last document associated to this new policy is the PMP index. Is a standard with inside the list of all the commercial grades approved in the Stellantis world, to which are associated the GPC codes. Then, moving to the green strategy, so the main focus, the currently main focus of Stellantis is the mechanical recycling, because it's at the moment the most diffused and also the cheapest technology available. The other possibility that we are evaluating and at the moment not so implementing is the biofeedstock and chemical recycling, to which is associated the mass balance approach. These kind of materials are not so used for several reasons. For sure, we have the cost. And the other reason is that this kind of approach, the mass balance one, is not so well, I can say, seen. Also because the regulation currently is not well detailing if it will be accepted or not. For example, in evaluating the 25% at the end of life regulation will oblige us to respect in the future. No? So the hope is that the regulation will have an evolution and it will be possible to understand very well if this kind of technology is something that can be used to reach the target that the European Commission will give us. Then we have an example that we make with MIPE that is here with us today. this is another possibility, another potential approach of sustainability in plastic, the application of biofiller inside the plastic. In this case, we have the application of wood fibers. This is an instrument panel fascia that has been used in a Panda model. A specific event was dedicated to this model, and I can say that it has not been the only one activity that we did with biofiller, but I have to say which is currently the way in which we see the filler. No? So from the point of view of the CO2 emission are very good. From the point of view of the mechanical properties, we saw performances that are decreasing, no, so not at the level of the standard filler. From the point of view of the processability, they are bringing us some constraint, no, because we have to decrease, for example, the temperature of extrusion. From the point of view of the chemical resistant aging, we have the same properties as the standard technology. So we are interesting, we are using them, as I showed you in the example, but obviously we cannot use them everywhere, okay? Then I will jump to circular economy. As I said before, this will be something that will be imposed also to us if the end-of-life regulation will be as it is currently in the draft version. And this is probably you know from the newspaper that last year was created here in Italy, in Mirafiori, in Turin, the first circular economy hub of Stellantis. Inside this circular economy hub, we have different activities. One is related to the vehicle reconditioning, so vehicles that are reconditioned and then put in the secondary market. We have the vehicle dismantling that is starting its activity to recover parts to be sold or to be recycled. And then we have the partner manufacturing that could be done internally or through the warehouse that is working as sorting center are remanufactured by external suppliers. And the last activity that is ongoing is the remanufacturing of the end-of-life batteries. Obviously, in this case, the batteries, due to the fact the numbers are not so huge, are not so much, okay? Then now I will show you a short video about the Mirafiori Hub. Okay, we are at the end. So last point of my agenda that I will touch is regarding innovation. And I will start describing you some of the innovation projects on which we are working, innovation projects that are linked to the Europe funding. One of them is the Plus Plus project. This project has been closed, but was dedicated to the reuse of the materials coming from the shredding of the full cars. The materials were sorted based on their density. With this project, we realized the component that you see in the picture. There's loudspeaker support made of ABS. Again, also in this case, it was thanks to a collaboration with MIPE. And then we are working also on the polyurethane biofoam. With this project is called Biomat. In this case, we would like to develop a polyurethane foam for the seat cushioning application and the steering wheel. We have another collaborative project called MyFi that has the aim to develop a skin based on the fungal fermentation that we have the aim to substitute the leather for interior application. We have this other project that is called Life Green Vulcan that has the focus on the recycling of the tires at the end of the life with a specific devulcanization process. And another project called Viable on which the scope is to try to use lignin and in alternative to the bisphenol A in the epoxy resin. Then we have Eolo Hubs, in which we would like to recyclate the material coming from the turbine blades at the end of the life. And then the last one that I will touch is like Beyond, in which we are working on several activities to make more green our vehicles. So I'm going to the conclusion. As I say, the carbonization and the circular economy are pushing us to research new green materials. We would like to have also legislation more clear on which kind of technology are allowed. And as you can imagine, we have to develop recycled biopolymers and filler with good performances, but also it should be at an acceptable cost, potentially, if possible, at a low cost, because as you see, as you know, automotive sector is very, very competitive, especially in this period. Okay, I'm done. Thank you.
Thank you, Gabriele, for your interesting presentation. So unfortunately, we are a little bit delayed. So if you don't want to miss the coffee pauses, we have to speed up a little bit. So maybe also for the question, I remind also that later maybe. Thank you again. So Röchling Automotive has been focusing on biopolymer and the recycling material for more than 10 years. So I will also welcome to Alessandro Iviglia, Matteo Traina, and Francesco Viola. So Alessandro Iviglia in particular is working with 20 years of experience, 14 years in the OEMs like FCA and Alfa Romeo. He have done also product management and product and development of plastic parts for automotive business. And Matteo Traina, and now he's working also for sustainability team leader global for Röchling. Matteo Traina is material engineering with 20 years experience in the plastic. Now he's working as a raw material specialist. And Francesco Viola is an aerospace engineer with 15 years experience. And now he's working as a global FMEA specialist and also leading LCA project and methodology. Thank you to be here. So I asked a little bit to make it faster, if possible. Thank you.
Okay, so good afternoon to everyone. My name is Alessandro Viglia, and starting from July of this year, I'm responsible sustainability global for Reckling Automotive. So, a quick view of our agenda of today. So I introduced to yourself our roadmap for sustainability in the future. Then some requirements from our customers, like, for example, LCA. So today we will have a focus on our product line, let me say. And then the sustainable materials that we're working with our customer. As more of a view about Reckling Group, because Reckling is a big group, it's a German family, from a German family. We are divided in industrial, automotive, and medical. And we have more or less more than 11,000 employees around the world. So we cover the production around all the world. And sales on more than 2.5 billion euro in the 2023. So the roadmap of our company, because we have to fix a roadmap for our future, because we are talking about 2030. So the first step will be 2030, and the second one 2030. So we have to have in our mind and on our desk a dedicated roadmap in order to follow our sustainability plan. A small overview, so we are focused on produce plastic, because Reckling is automotive supplier and we produce components in plastic. So we have to use and to produce components sustainable for the future. In the meantime, to have in our mind the circular economy, as before mentioned, FCA Stellantis, circularity will be a pillars in the future, and promote further environment-friendly innovations, and at the same time also try to use as much as possible renewable energy for our plants. You can see, as I said before, 2030, 2030. 2030, the first step. For our goal is to reduce 80% of our total emissions. So today we are in the end of 2024. So in front of us we have 5 years to reduce significantly our emissions 80%, and in the same time to increase our energy efficiency by 50%. As Reckling Group, we are proceeding together in a strategy. Yes, for each division we have some pillars and KPIs dedicated, but we are dividing our activities in the product, people, and planet. What is important for the product? As I said before, circularity, recycled material, and especially quality for our customers. People, we have to follow also a sustainable workplace in the future. And workplace means to have a diversity, inclusion, and equal opportunity, and also occupational health and safety. And then planet. Planet is following the climate change. Following climate change means that, okay, we have not to say, okay, we follow and, okay, cross our fingers. No, work together to improve the possibility to decrease the trouble in the future following climate change. Product, people, planet, there are some of our KPIs that I was following. As I said, 2030, 80%, 2030, following SBTi program, so science-based targets, 100%, so net zero in 2030. For scope 1 and scope 2. As you can see, scope 1 and 2 and scope 3. Scope 3, it's something that we cannot directly control because we have upstream and downstream activities. But for scope 1 and 2, as Reckling, we can proceed with our activities and with our projects. Today we will talk about products and plastic. In Reckling we started 10 years ago to talk about biomaterial and recycled material. We have two families of material group. One of these is reloop. So all the material starting from recycled solution, or post-industrial or post-consumer. Today, in 2024, our global production use 30% of recycled material. In some cases, we have some components totally made in 100% recycled solution. And our goal in 2028 is to achieve 60% overall of our production with recycled material when and where customers require this. And now it's a pleasure to hand over to you, Francesco, to explain the LCA process.
Thank you, Alessandro. Hello, everyone. So, as said, introduced by Andrea before, I'm in Röchling, the one that is currently leading the LCA project. So I will give you a short introduction of what this project means. So in general, as said, also according to our strategy, we want to evaluate the environmental impact of our products and in order to reduce. But before to reduce, as said, we have to evaluate. The methodology we decide to use to evaluate the environmental impact is the life cycle assessment. As many of you probably know, the life cycle assessment, it's a methodology that allows to evaluate the environmental impact through all the products life cycle. So from raw material extraction to the end of life and disposal. So we, as Röchling, want to start evaluate our product. It's a project that we started almost 2 years ago. And the target we have at the beginning, it's a part of the last cycle. It means we want to evaluate at first the carbon footprint, the GWP. This means this will be the first step we will take, and afterwards, step by step, we will move to an evaluation of all the other impact categories. The GWP actually means that we measure the heat that is absorbed by the greenhouse gases as a multiple of the heat absorbed by the carbon dioxide. We are said before by Alessandro, are a global company, so we have to think globally and to have a global approach. That's why we decided to create a general model. Why? Because our facilities work more or less in the same way. We produce the same type of parts, and so we can produce with the same approach. That means especially a primary manufacturing and then some subsequent operation. In this primary manufacturing, we use raw material, and then we can either mount or not subcomponent outsourced part on our products. That's why we decided to identify where is the boundary of our analysis. This means we identified where is the primary manufacturing system, the material. We evaluate also the transport of this material, as well as the secondary. This means all the by-parts that we mount on our product together with their transport. We have to consider our production, and in our production means collect all the ancillary inputs, all the material that we have to use to produce our part that actually will not be in the part itself. And finally, after assembling the part, we have to consider also, and this comes to material as well, what is the packaging we use, what is not reusable packaging that we are using to transfer our products among our plants, because we have parts that are produced in different plants, and to the customer. So to evaluate this impact, we have to use our ERP system that allows us to collect as many information on product as we have. And so we have to consider also what comes from the supply chain. For this reason, we use an approach of creating a model that evaluates this contribution, where we both collect primary and secondary data. Primary is coming from our production system for the manufacturing part, while for the supply chain, primary data are coming from supplier. Of course, in some cases, we cannot get this value from our supply chain, or it's not so easy to initially detect and measure in our facilities. And for this reason, on that case, we use secondary data coming from database. But to have this, we have to use, of course, an LCA software. We identified the Sphera LCA for Expert as our software. And so we create an interface between this software and our ERP system, where data that are primary we can collect in SAP, and SAP will communicate to software for the for the inventory. And whenever the data is not available, the software, the model we created for software is able to take from the software database itself that value and provide to the calculator. Finally, we are able to evaluate the environmental impact of the product that, as said at the beginning, in this stage will be the CO2, so the carbon footprint. And we are able, as we have a general approach of a general model, to have a general report where all data that are changed are actually data related to every single product. So whenever there is a product, the ERP system communicates to the software and writes also in the report the information related to that product. Finally, we get a report, and the report will be used for internal storage, because from our strategy from 2028, we will calculate for all our products, but also for customer sharing and, if required, for certification. So that's all from my side. I will hand over to Matteo.
Hello. Thank you, Francesco. My name is Matteo Traina, and the last part will be dedicated to what is one of the key pillars of our company, meaning that we are plastic guys. We develop product, meaning that the very first thing that we know we need to manage is to be aware about the material we use. In particular, if we try to pursue solution to get sustainability, is also to select the right material. This apply in the specific case to know exactly what is available on the market in terms of solution to get sustainability. I think the recycled material is the very first thing that you can have in mind. But since we are all people working on the plastic, we are conscious that there are also other solutions. With this solution in mind, the very important thing is also to understand that each solution has a different feature. Unfortunately, no one of these is the perfect solution which is able to put everything together: low cost, high performance, high sustainability footprint. Any of the solutions that we have on the market is affected by some drawback. If you won't spend, you have the perfect solution because you have the biofeedstock-based material using mass balance. On the other side, it means that everything is costing more. If you have recycling, you don't have the perfect technical solution because you are suffering or some low reduction of the performance. From the practical point of view, this means that the development should be oriented to take into account exactly what is the requirement related to the part that you have to manage. And look back to your book to understand what the plastic can do and put the requirement all together and find the right solution. This integrated approach brings to different comment about possible product that we can consider. Here, I had a short view about the product that Rockling is managing. But let me say that for any application, it works in a similar way. For example, for underbody, the part on my right, you can see that the critical item is to have material able to work properly in the process, meaning to fill the molding during the injection molding, a good resistance to low temperature. This brings that the possible solution is recycling. There's mechanical recycled material. On the other side, you have to take into account to select a material which is not suffering in terms of impact resistance reduction. If you consider a material that you use for climate cabin air duct, over there, the mechanical requirements are relatively poor in comparison to other applications. On the other side, you have a particular requirement that sometimes the people don't think about it. This is the contamination can bring to have a pollution to the moisture, which is causing an odor which is not appreciated by the people. For this way, you could select a recycled material, but you have to put a lot of care to take the right one. All the product applies in a similar way in this analysis. For example, there are also products where the use of recycling is not matching at all the technical requirement. For example, the bottle which contains the liquid for the cooling system are suffering of big requirements which are not compatible with the typical performance of recycled material. For this reason, the only way that you have to follow to meet the current requirement is to use a biofeedstock material based on mass balance approach. In this way, for any product, there is something to put on the table to consider in the right way if the recycled material is the right solution, meaning if it is able to match the requirement. Later on, you have just to manage and understand what is the best one. Sometimes, let me say, all the solutions are possible, but you have to manage some drawback. What you get in terms of performance, you get also in terms of cost. I ended with my part, so I give back the microphone, the stage to Andrea.
Thank you. I think we save a little bit sometimes. I appreciate it. So for the question, I think also we can wait later. Okay, thank you. Thank you again. So I don't want to introduce company MIPE. You already heard something about that before. But I also would like to introduce Gianluca Pizzati. Gianluca is an expert with more than 20 years experience in high-tech polymer compounding with focus in the automotive field. Along his experience, he dealt with topics related to material development and also for specific applications for the components. He's working now as a CEO of MIPE Compounding, and I'm really thank Gianluca to really very interesting presentation. And
too long description. It means that I'm too old.
You know we have to make faster. Okay. Thank you.
Okay, so a few minutes just to introduce a little bit MIPE. First 4 or 5 slides are dedicated to that, but Eligio already told about that. And anyway, it's quite an old company, starting activities in 1960, so a lot ago. What is important to underline is that it was starting the business as a distributor. Today, the main activities are in the compounding and in the polymerization. Compounding of several polymers, we will see later on the portfolio. And of course, let me say what is more important, even the production, the polymerization of the PHA. Here you see some figures which can be interesting. Compounding sites are 2, one operative in Settimo Torinese and one ongoing in India. Automotive is the main business because it's representing more than 60% of the total sales. Why we think MIPE can be interesting for our customer? I think that there are some good reasons explained here. Basically, tailor-made co-design support, quite, let me say, wide portfolio of green solution and prime grades. Plus a special, let me say, experience because we are polymer producer, PHA compounding producer, as well as we have a very strong R&D and the distribution, which is in any way something which is important for us. Here you see the product portfolio. What you see in orange are basically traditional material, prime grade, wide portfolio of products from polyamide to polypropylene to PCABS and blends in general. Then we have some innovative compounds. In this case, what is important is not the material family, but the property, which are conferred to the material. One example is Diamond, which is used today in Stellantis as a black piano product, which is a substituting material which are painted for exterior, for example. We have the green area where we are, let me say, traditional recycling, mechanical recycling products. We have chemical recycling products and biopolymer from our production, PHA. And another point which is extremely interesting for the automotive field are the special effects. You see on the table where we are located here a part which is realized with a very special effect with some sparkles. This is something which is very interesting to get rid of painting and grant personalization to the car. So let's talk now about green polymers and the challenges and the opportunity that we are facing to enter in this world. This is the view, an overview of the future in plastics. Despite everybody are saying bad words about plastics, at the end plastics are still continue to growing and it will continue to growing. Here we have a prevision of 2050. So what will be totally different, maybe it will not happen in 2050, but for sure in the future, is that we will not produce plastic anymore from fossil-based feedstock. We can do it already, but the problem, technically I mean, but of course it's impossible to get rid of fossil base today because of the plants, because of the, let me say, investment that have to be done to arrive to this target. But in the future, we will have recycling as the main, let me say, production way to produce plastics. That's something which will include the mechanical recycling and the chemical recycling, which probably in terms of dimension will be the easiest and the better solution to recycle without separation the different plastic material. We will have a relevant amount of bio-based polymer, which can include PHA, PLA, and other products which are already existing. And we will have a relevant part that today is almost representing zero, which is the production of polymer starting from CO2. So basically, we will take CO2 from the atmosphere to produce monomers. A concept that sometimes is not clear to the people. Today we are focusing, even our colleague Stellantis, about LCA, so the target is to reduce the carbon footprint of the material. But if you look just to CO2 emission today, the only, let me say, positive or reliable solution is the mechanical recycling that have a certain limitation in terms of mechanical property and so on. If we consider the overall, let me say, circle of the economy, sometimes we have solutions like the chemical recycling that today are, in terms of CO2 emission, higher than a traditional polymer coming from, let me say, oil. And that's something which we need to clarify, because if we want a real circular economy, we will have to consider the LCA or the carbon footprint under a different view. So in the short term, probably we will have to accept to have a CO2 emission higher to compensate the fact that we are using a material in a real total circular economy. In the future, when the energy cost in terms of CO2 emission will be zero, it will be possible to have a circular economy granting even a positive value of LCA. But today, sometimes these two concepts, which from a theoretical point of view have to go in the same direction, are fighting each other. Here you have basically a circular economy, let me say, graph, indicating what happened in an idle circular economy of a material which is coming from oil against a material which is coming from renewable. The concept is not too different. In the future, probably the renewable part will be more and more. Once again, it's not a technical question. Today, you can realize probably already, from a technical point of view, 70% of the polymer starting from a renewable source. But of course, the plants are not ready, and there's not enough feedstock coming from renewable source. Another point to consider is that renewable sources are sometimes vegetable, often vegetable. And this type of source are, let me say, or can be, let me say, in the same line of the food chain. So, do we want to produce plastics from biosource or in alternative food? So we need to look, let me say, for a reasonable compromise. The key objective of the circular economy, I think that which here everybody probably will agree, is that we need to be able, let me say, to go to a real circular economy. I don't know if for 2030, maybe it's too short time, but maybe for the future, we need to think in a new way. So green design, the one that have been, for example, explained from Stellantis, talking about the solution full polyester can be a good example. So we cannot imagine to use a recycled material with a traditional design, or not always we can do that. We need sometimes to adapt the design to the material. That's very important when it comes to mechanical recycling. Like, for example, polyamide coming from textile. Normally, you have a certain amount of titanium dioxide in, which means that you have a technical performance, especially tensile strength, which are lower. And the solution is to use not this grade for a high-demanding material or parts, but another solution is simply to increase a little bit the thickness. No? So design is extremely important in combination to the material. Another very important point will be supply chain, because today, when it comes to mechanical recycling, we will see later on some slide, we are in reality recycling a small amount of polymers. The majority of the plastic is waste and used or burned to produce energy. And that's a problem if we want really to arrive to a real circular economy. So new technology, of course, will be a key, as well as certification and so on. So from a LCA point of view, instead, what we need to underline is that today we miss information, or at least, let's take an example. We are producing polyamide and we have two suppliers. One is European and the other one is Asian, okay? Which is normal because we need to have source from different parts of the world to minimize the risk of break into the supply chain. The thing is that in our final compound, we can have a difference in terms of LCA, which can be from 30% to 40%, because the production in China is a lot higher in terms of LCA value in comparison to the European one. So which is the value which we have to give to Stellantis if they ask to us, or to a customer if they ask to us? One of the two. So we need this information. We need to, let me say, escape from the logic of the database with general information for which polyamide 6 is having a LCA of 7, 8. We need more precise value. So that's one point very important when it comes to LCA. Regulation. Regulation is very important because you can calculate LCA in a completely different way. You can calculate it in the whole life of the part, or you can calculate LCA just in our production process, in your production process. We need rules to, let me say, establish a single way to analyze and to compare into the market. Today, there's a lot of confusion from this point of view. So very important to analyze the total life cycle of the part, as well as we need to consider that, as I told before, sometimes there are solutions like chemical recycling, which can be very good for circular economy, which is not the same, or today they are not the same in terms of LCA value for what is concerning reduction of CO2 emission. So what we need is like to create a paradigm, a new paradigm, in which we, let me say, we melt or we consider a solution which is, let me say, not a single solution, but a systemic green way, okay? So we need definitely mechanical recycling because it's the cheapest and is the easiest way. It's traditional because we are producing mechanical recycling compounds since 30 years. And of course, that will be in any way the best solution for a LCA point of view and from a circular economy point of view. It's the only way to produce green material, let me say, keeping in count both the two, let me say, needs. We must solve the problem of the CO2 emission and the, let me say, the circular economy. And in my opinion, as I said, the future is definitely more to look to a circular economy more than simply to the CO2 emission, which is a concept easy to sell to the customer, but sometimes not the best one if we are looking for the environment, to the environment. Of course, there's not a single unique winning solution, and we will need a different technological, let me say, approach in order to be able to grant a sustainable future. So we will need, let me say, a concept or a solution which will involve recycling. We will involve carbon capture and the utilization of CO2 as a monomer, as well as the biomass or the renewable source. That's a description of trying, let me say, to describe the problematic of the recycling. Today we are collecting, here we see some example of material. We are collecting just few material. And in function of the collection, in function of the feedstock, in function of the, let me say, grade of separation and contamination, we can imagine to use this material in different process. Here you see something like glycolysis, which is an easiest process, less demanding in terms of energy in comparison to traditional pyrolysis, but you need to use basically polyester or even just PET. Methanolysis can be another solution, is another chemical, let me say, technology, but is okay, or it can be used just if you have a polyester feedstock. If you have a contamination, then you have a problem. And of course, there's traditional pyrolysis, which is, from an industrial point of view, the easiest way to collect material, because you can, let me say, get all material all together, plus the organic fraction, and simply burn these scraps to come back to an oil which is not coming anymore from, let me say, not renewable source, but we can consider this oil coming from renewable source. This is the situation in Italy today, but if you look to Europe, it's similar, okay? Those are values of 2023. So when it comes to recycling, we are already recycling big amount of material, because just in Italy, it's more than 750,000 tons, a lot. And of course, if you look to what I was telling before, you will see that what we are today mainly reusing is PET and polyolefin. Okay? If you look to polyolefin, MPO means mix of polyolefin. Recycling PP, and you have recycling PET, HDPE, and polyethylene. If you add this material, which are basically polyester and polyethylene, you arrive at 96% of what we are recovering. So all the rest is just 4%, almost nothing. Because when we are here talking about automotive, we have a big consumption of PBT, polyamide, and so on. So today, our, let me say, way to recycle is limiting mainly to material which are coming from, let me say, packaging. Here you see from which the material is coming from. And you see building and construction, of course, you have, let me say, quite a good use of recycled material. The packaging is, let me say, is working pretty well because it's making, let me say, waste, but it's reusing waste. But if you see technical, let me say, use, there are not a big consumption still, so there are space to grow. But the reason why we have a limitation is that we have a limitation in the collection of the material. Looking to market segmentation, okay, to evaluate the market of recycling, you see that 70% more or less, so a big majority is coming from our, let me say, waste at home. What I call here city waste is basically the collection of our local community or city. And then you see B2B means business to business packaging, which is recovered and it is quite a relevant amount. Agriculture still, let me say, a relevant segment, but all the other is almost nothing. Once again, the problem is that we have not a reliable supply chain. This is the area where we have to focus for the future. Here you see, taking account that here we are talking about something which is changing day by day. But still, this is a picture of the situation today. What you can have post-industrial, what you can have post-consumption, what you can have bio-based, what you can have from chemical recycling. PP, you can have even already few amount bio-based, but is not relevant. In the future will grow. Polyamide 6, same story. You can have quite a good amount of post-industrial material, but you have almost nothing when it comes to post-consumption. Just few polyamide 6 maybe coming from fishing net, but there are not a real collection of post-consumption for polyamide 6. So we can make maybe a business case granting post-consumption, but if you look to big volumes, today we have to consider post-industrial at the same level of post-consumption, otherwise we will have a big problem in order to satisfy the requirements. There are other materials for which you have almost all solutions, like ABS, there are already bio-based or partially bio-based solutions. You have chemical recycling, the same is for polyester. Polyester world is one of the easiest in terms of chemistry, where you can have all solutions, post-industrial, post-consumption, and bio-based, and chemical recycling too. Or this is, let me say, a fast description trying to tell how much material coming from mechanical recycling or recycling I can use to grant property which are similar to prime, okay? So in some cases, you see in case of polyamide, the amount of recycling, if you want to grant mechanical property which are close to prime, are not so big because of the titanium dioxide, which I was mentioning. 70% of, let me say, polyamide recycling is coming from textile industry, which unfortunately is adding, for different reasons, titanium dioxide, which is breaking the fiber. There are other materials for which you can use a higher amount, like in case of PBT and so on, or ABS-PC, in which you can use almost 100% components of polycarbonate coming from recycling. And then same story is for colorability and aesthetics, because there are material for which is common to have base which are not colored, and so you can imagine even to realize colored compound. And there are feedstock where you have a mix of color, and of course you cannot imagine to make other colors than black. So there are, again, different ways. The recycling is the king. We have chemical recycling, we have mechanical recycling. We can have hybrid composites, which are based on material recycling plus some fiber, which are natural, so coming from a renewable source. We have biopolymer and under development, because today there are not many examples, CO2. Here you see more in detail some solutions, which are the one that we are proposing to the market. Life 2 is mechanical recycling, Quid is hybrid composite, and Cerbio means chemical recycling biopolymers. And we have some solution based on the agreement with Eastman, as well as another way to reduce purely the LCA is material based on UBQ technology. We will have a slide. Which is the limitation of mechanical recycling. Mechanical recycling, as it was mentioned, of course, it's having big limitation because of the mechanical property, because of the feedstock, which cannot be controlled 100%. So the key of a good mechanical recycling process is the feedstock, the quality of scrap. You have a degradation limits, which is the number of cycles or recycling cycles that you can have with the material. So you have a strong limitation in case of transparent product, which is almost impossible to be realized if not accepting black spot as a, let me say, with the big presence of black spots, and maybe even yellow index variation. Mechanical property, of course, there are a strong limitation. So basically, to succeed using mechanical recycling, you need to dedicate, because the volumes are limited, you need to dedicate in partnership the source and the products, the amount, in agreement with the customer and the application. So you need to grant the customer, and this is function of your supply chain. You need to design the part to use this material. That's a key, because then we cannot complain if the properties are not the same of prime. We know it from the beginning. And the key is definitely the mix between post-consumption and post-industrial, which is different material by material in function of what is possible to receive from the market. Feedstock control, so, is the real value of every company. What will be, and where today there's a big mess, but I hope in the future it will be something more clear, is that everybody are claiming to have green material, but what's important, in my opinion, is to have certification. Today, there are not one common agreed certification, for example, for Europe, but there are third party like CSC or CSI or TUV, which are granting, let me say, the real amount and the, let me say, the provenance of the material, if it's PCR or PIR. That's a key, and is, let me say, definitely our way to go green. I finished my time, so I try to speed up as much as I can. Another way to, let me say, reduce the amount of LCA, the value of the LCA, is to use a traditional polymer, in this case just polypropylene, with some natural fiber. Here you see an example which is in serial production. Chemical recycling is another way, which is the problem. Once again, supply chain, big investment. The advantage is that you have a quality as prime, of course. It's easier, the supply chain, in comparison to the mechanical recycling, because you do not need to separate too much. You can take, in many cases, depending on the process, different type of scraps altogether. Is in full respect of the circularity, but today, unfortunately, is having an LCA of the final products because of the energy consumption, which is higher, okay? And the investment is big. We are talking about big investment, which in the moment are just able to cover a limited amount of what the market is needing. Here you see different, let me say, type of chemical recycling, which are using, going from right to left, more energy. As much as we go left, and as worse will be the LCA of the material. because we will need more energy. As much as we will be, like in case of the mechanical, let me say, recycling, which is simply the reuse, okay? And the better will be the energy use. So you see what we can have today already from chemical recycling. We have some serial production of this product too. Is mainly copolyester, some polyamides, limited quantity, ABS as well, and polyolefin as well, not a big quantity. We have some solutions which are based on today Eastman carbon renewal technology, which are mainly recycling polyester, material which have the same property or similar property to polycarbonate and polycarbonate ABS. Unfortunately, not for the same cost, I have to say. I was mentioning before how to reduce the LCA using prime grades and adding something which is able to reduce the amount of LCA value. This is cycle zero, what we call cycle zero, which is basically an additive which you can consider as a mineral filler, even if it's not mineral. Basically, is an additive that you add to put with a negative, let me say, LCA value. And so as much as you add this additive to your polypropylene, for example, and as much as you reduce the LCA of the final compound. You can consider this material as an alternative to PP talc, for example, with some limitation like odor, because here we are talking about scraps which are coming from the waste of the city. So even if the material is partially pyrolyzed, you still have some organic remaining presence. Bioplastic, it has been mentioned. I think that Eligio already mentioned our products, so I will pass through quite fast. There are several materials which can be realized from renewable source. You know the difference, I think, from biodegradable and, let me say, fossil-based and bio-based. So sometimes there are confusion definitely into the market and definitely into the consumers, okay? Bio is used from everything. Mechanical recycling, bio-content, biodegradability, that's not true. We need to clarify this point. So that's what it's really biodegradable. So I'm naturally, our PHA is one of the solutions in this area, the only solution which can be used and able to degrade in uncontrolled, let me say, environment, which means open water, soil, and marine. The majority of our, let me say, polymers can biodegrade just maybe in industrial compost, for example. The key of this material is that it's able to degrade even in uncontrolled environment. Here you see a comparison with other materials. It's a slide that I think Eligio already presented to you. Those are some applications of this biopolymer. As you can see, there are even durable applications because it's biodegradable, but it's biodegradable as the wood, okay? So the wood, we are producing furniture based on wood, and this furniture can stand for 1,000 years. That is depending on the environment. The same is for this material. That's it.
Thank you, Gianluca. I know that your presentation was really interesting, but also challenging from the other perspective. So before the coffee, so we have the last speech of our first section. I would like also to introduce Gabriele Baratella. So maybe someone of you know already company Aquafil. Aquafil, now we change a little bit the perspective to a textile product. Aquafil is a pioneer manufacturer of circular plastic, starting from the recycling of the fishing nets. So, Gabriele, also we have to run a little bit, no?
Okay.
Then
okay.
The stage is yours. Thank you.
Thank you. Good afternoon, everybody. I'm Gabriele Baratella. I've been working in Aquafil Arco. The headquarters are based in Arco since 1999. Aquafil Group is a manufacturer of nylon 6 fibers and polymers. And we are a pioneer in circular economy and in recyclable products because our flagship is Econil. Econil is recycled nylon 6. And I want to show you in this short presentation, the time that I have to my disposal, how we will use this recycled polymer, chemically recycled nylon 6, to develop together with our customer the concept of circular economy for their products. So here you have a scheme of what is the linear economy, so from cradle to waste. A recycling economy, which means basically reusing the polymer or the product as much as possible, but something will anyway go into incineration, landfilling, or whatever. And circular economy, whose scope is obviously to recycle every possible component of this product and infinitely time. So ECONYL. ECONYL is a chemical recycled nylon 6. So I don't want to go deeper in details because Gianluca has already explained very well the different types of possibilities in terms of recycling. What I wanted to just highlight is that this type of polymer is, as said, a chemically recycled one. It's made using nylon 6 waste that we collect all over the world, both post-industrial and post-consumer waste. For example, fishing nets, fabric scraps, or carpets. Why carpets? Because our major sector of application are the flooring industry, both for automotive and for other applications like offices, heavy duties, residential, hotels, and so on. And so when we started with the chemical recycling of nylon 6, obviously, the first idea was let's try to have back what our customer are buying from us, and so the carpets. These are the carpets that are disposed, landfilled during a building renewal in the US. We are selling yarn in all continents, not only in Europe, but also in Asia, in the United States. And as you can imagine, the carpets are very often used in habitation in the US. And once someone comes new in an habitation, the first thing that is changed are the carpets. There are some states, some countries in the US that are giving subsidies in order to avoid the carpets to be landfilled, but given to collectors that are then conveying this carpet to our recycling center based in Phoenix, Arizona. This is the warehouse that we have in Slovenia, where we collect all the post-consumer waste that we collect all over the world. As you can see, there are carpets, yes, but also a lot of fishing nets, as already mentioned by Gianluca in the previous presentation. These are pre-handled. I mean, we are not receiving fishing nets with shells, fish, or whatever you can collect from the sea, but these are previously cleaned, and also even if these nets are 99% nylon 6, there are some ropes in polypropylene or some iron rings and so on. These are previously removed on site. We have a collaboration with Northern Europe collectors like Nofir, for example, that takes account for the northern countries in Europe, like Norway, Sweden, Finland, and so on. We have another one in Chile, for example. This is a fundamental step for our process, not to receive the ware as it is, the waste as it is, but a little bit pre-digested by someone. Yeah? Then there is a mechanical pre-treatment of these products. This means reducing them in small pieces and possibly also separate contaminants. With contaminants, I mean polymers which are not nylon 6. because as already highlighted in the previous presentation by Gabriele, most of the products that we receive are multi-layer products composed by different types of polymers. We are able, through our chemical recycling process, to recycle nylon 6. The rest must be decanted or treated in a different, by different methods. What is the result? The result of this is, as you can see here, we have a primary yarn, so the comparison between a standard way of producing a yarn or a carpet in a nylon 6 and what happens with Econyl. With a primary yarn and looking into the perspective of the LCA, we start for the oil extraction, several chemical steps in between to arrive to the production of the monomer, which is the caprolactam, and then the caprolactam is polymerized to nylon 6 and then spun into yarn and used for the carpets. In the case of Econyl, we recover the nylon 6 waste directly from the market. We go in a depolymerization, chemical depolymerization of nylon 6, which from the chemical engineering point of view is catalyzed hydrolysis with a following step of purification based on distillation, like a grappa. So we remove the top, the bottom, just taking the core and removing in this case all the contaminants. Also because one of the biggest advantages of the chemical depolymerization of nylon 6 is that it's happening in a gaseous phase. This means that all the contaminants that are inside, like pigments, stabilizers, everyone just fall, simply said, by gravity. You don't have to have a real filtering like it happens, for example, for the chemical recycling of polyester, PET, not polyester, or PET, that is happening in a liquid phase, so a part must be always filtered, and this is obviously more difficult. The results of the Econyl, which are then certified in the, through an LCA system, and so resulting in an EPD, so in environmental product declaration, can be seen here. We have up to a 90% reduction of the global warming potential and up to 65% reduction of the primary energy demand. We are suppliers of nylon 6 yarn, so as far as the automotive sector is concerned, this means the textile interiors. So molded parts, back trunk, front trunk, side panels, back seat panels, car mats. Why car mats now? Because looking to the principle of the circular economy, we focused our attention on a product in the car for which we are supplying our yarn, which can be easily removed by the car, which has a short lifetime, so can be really reused. And there is point of exchange at the OEMs, which are theoretically already possible. One of the key factors of the recyclability of any product is the so-called reverse logistic. So having back the material. So for the car mats, for example, the theoretical possibility is that in the shops where you can buy a new set of mats, dedicated shop, you will have the possibility to bring your old mats back and have a new set of recycled product. A carpet, how is composed the carpet? A carpet is composed by a nylon 6 top pile, then there is a primary baking which can be in polypropylene or PET. Then there are some coating, glue, and secondary baking that possibly are also filled with calcium carbonate or other type of fillers in order to have a more stiff product. The idea is to work with our customer, with the tier 1 of the automotive industry, in order to have a carpet where you have the face pile, which is not Econyl, obviously, and the secondary baking in a polyolefin that can be then mechanically recycled, so like polypropylene or polyethylene. The result of this product is that we processed together in collaboration with some tier ones these type of mats, and we succeeded in separating the face pile and nylon 6 from the baking in polyolefin and recycle both of them in a new product. So the nylon 6 directly in our Econil plant in order to have a recycled nylon 6 fiber, and the polypropylene, for example, mechanically recycled, having two products that can be reused to make the same product again. So why the tier one was really interested in such a product or in such a process? Because it offers a real closed-loop solution. The mats were returned to us. We were able to separate the nylon 6 from the rest and recycled the same nylon 6 chemically, the polypropylene mechanically, to have polymers that can be reused to do the same, so yarn to yarn, fiber to fiber, again. Looking at the shape of a car mat, you can see that it's not a regular shape. It has different shapes, resulting in a lot of trims. A tier one for the automotive industry producing mats can have in their production up to 20% of trims resulting, depending obviously of the shape of the mat. So if the final product is recyclable, also the semi-products are recyclable. And so also for the tier one, you have an economical value because instead of landfilling, incinerating the scraps, they can return to us and we can recycle it. The idea is that this sandwich, this multi-layer product, is composed by polymers for which there is a safe and sound supply chain. Because one of the approaches that we are experiencing also in the textile industry is a rush to monomaterial PET. But for the time being, recycled PET is mostly in the hand of Chinese or Indian suppliers, whereas nylon 6 and polypropylene are also easily recycled within Europe. That are the basic points that awake the interest, raise the interest of OEM and tier one for our product. We have already a product which has been validated, approved, and the first SOP in the automotive industry will be next year with a product like this, and we hope that more and more tier one and OEM will join us because this is offering really a closed-loop solution. Thank you for your attention.
Grazie, Gabriele. I think we need a break, so even if it is a little bit delayed, but I think that we can use 10 minutes to enjoy the coffee here and also drink some water and don't forget the network. Please enjoy. Thank you. Hai recuperato qualche... Hai recuperato qualche minuto, sì. Perché siamo partiti? Adesso se non mi tolgono sta frase. Oh, lo so. Non posso dire. Ok, siamo pronti? Che scarpette. Okay, we are start for the second half of the day. We have a presentation about some tools now. We have the additional tool and solution for as well as eco-design method. So let me introduce Silvia Di Rosa. Silvia Di Rosa is graduate with material engineering with 16-year experience for company in the Fiat Stellantis group. Today, she deals with business development, engine soft simulation and software solution. So please, Silvia, introduce how software can help us choosing the right choice about Polite. Thank you.
Thanks a lot, Andrea. Thanks to all. Thanks for the invitation. It's a pleasure for me to stay here in Neupark Südtirol in Bozen. Today I have met different friends that were part of my past life, university, and also in Turin, Fiat Research Center, so it's a pleasure for me to meet you here. My presentation has this title, Strategies for Environmental Sustainability Through Smart Material Selection, Focus on Polymers. I am a material engineer. I work in Engine Soft. Engine Soft is an Italian company that has changed last year because following a corporate reorganization inside the societary assets, now we have a Brazilian company that is called E3+. And this operation has created a worldwide group with all the branches that you can see in this slide, with more than 2,050 customers, 400 engineers involved in the business, and 20 offices around the world. We sell software, we sell training and education, and we sell services. The tool that we sell and the main product for our business is the ANSYS platform that is one of the most important worldwide. And the ANSYS platform has inside structure, fluids, electromagnetics, and semiconductors, embedded software, and the optical tools. Over time, we have seen an increasingly dedicated and rigid path in terms of regulations. Only some important topics in this path: the Kyoto Protocol, the European Green Deal, and the International Energy Agency released a roadmap in 2021, and we have the objective to reach within 2050 near zero emission. It's a very ambitious target, but now we are discussing about plastic transition also because we have a target like this. Let's focus on industries. My presentation is focused on industries and on the challenges that inside the company we have to develop and to bring out. The materials compliance challenges is the main objective of my words. Material choices are increasing dramatically. You can see in this graph the increasing of the available material that now we have in the market. There is a continuous increasing in restricted substances and in regulations. And the cost of changing materials rises over time. The intelligent choice of materials for our production must be placed in the early stage of the production phase, because only in this way there is a lower economic impact. The sustainability decision has an impact, a direct impact on business. We have to reduce time to market, to increase cost, to increase quality, to reduce cost, and it's always important to improve the brand awareness. We have to consider the whole life of the product, from the extraction of material to the end use phase, and also the recycling or recovery phase. Sustainability decisions in early product development create material impact on production and use. Already, someone before me has discussed about the life cycle thinking and the circular economy. So now we have to discuss about the circular thinking in the production phase, starting from the design and the concept phase. Choosing the right material is business critical. We have to control cost. In which way can I perform reliable simulation? What's the equivalent grade for manufacturing elsewhere? In which way I can find the materials that allow me to spend the lower cost? Then we have to increase and to boost the revenue. Can I innovate with new material? How can I lightweight my product? And also we have to mitigate the risk. The regulation regarding restricted substances are very, very rigid, and we have to respect them. In the platform ANSYS, there is a specific tool dedicated to materials that can help us in the plastic transition and in the material challenges. Materials information is one of the fundamental inputs for our simulation. If we put the wrong material properties, we don't have correct results in the simulation with the finite element. ANSYS Granta is the product that ANSYS has acquired from a Cambridge company that was founded by Professor Ashby. For a materials engineer, Professor Ashby is very known because he was the man that has created the Ashby maps. In the the following slide, I show to you an Ashby maps. He was the first that created a graphical form to represent the material property in a space XY defined with specific properties that the user can underline. So here in this slide, only a few products of the Granta platform. There are many different products from the entry level, that is Granta Materials Data for Simulation, and so on. There is also a PLM that is concentrated on materials management, and it could be integrated with all the commercial PLM that we can find on the market. These are the whole libraries that Granta offers. So we have a very, very rich database of material that can be used as the base of our research. This is an Ashby map. So here you can see in which way materials can be designed in this graph, where we have on X price and on Y CO2 footprint. So we can make a direct comparison among different materials. With the Ashby map, we can create projects in order to find alternative material, alternative to our normal production. So we can put some specific condition, boundary condition, and we can find in a very easy way alternative to our normal production material. I can go slow. In our database, in Granta database, we find also a series of information that are directly connected to sustainability. You can see in this slide some of these, and to the compliance with the legislation. We have also relevant data for circular economy regarding the geoeconomic data that can allow us to discuss about availability and supply chain, energy and CO2 data for material production, processing and recycling. We can create an LCA with this tool, so we can consider the different phase of the production stage from starting from the extraction of material. And then we have information on the end of life and renewable resource. We have also the recycle mark that indicates whatever the plastic used in the production can be recycled into new product. Inside the recycling logo, we have different number from 1 to 7 that are connected to different polymers materials. Another very important thing is that we have to analyze in a critical way all the lines of our bill of materials. And it's not so simple work for the colleagues that are in the quality office, because they have to know all the regulation, the legislation, and they have to find if there are some lines of the bill of material that is out of this legislation. If we work with this instrument, we can have a final summary report like this in this slide, where we can see an X red if the specific line of the bill of material is out of legislation, or a flag, a green flag, if it's okay. So we have immediately a photo of the compliance of our product with the different regulation. Some testimonials, one that is very important, Rolls-Royce, said that global financial benefit using this type of instrument has been certified at $10,000 for each year in time saved, optimization, and reduced waste. Because simulation in general and in specific material simulation can help us to reduce time and to improve our revenue. This, we can go on. This is an example that we have made for a company, an Italian company that works for packaging, a very important company. And they had to reduce the carbon footprint of material used in packaging for electronic components. We use the ANSYS Granta tool, but only to show you the procedure that we can follow. If we have a specific tool, we create HB maps, we create different boundary conditions, and the benefit was to improve time to market, because the designer, the engineer, identify candidates for alternative material very fast, in a very fast way, and they reduce carbon footprint within 10% while maintaining mechanical properties sufficient for design. So putting a specific boundary condition in a very fast way, we can find alternatives using the HB maps. Other example, in a very fast way, because Andrea gave to me to reduce my time for the presentation. Some data regarding the production of plastic bottles, and we produce almost 20,000 bottles per second. And the life of plastic bottle in the environment are more than 400 years. So there are two solutions, recycling and energy recovery, but someone before me has already discussed about this. Here we have some world production of some bulk plastics, and on the right we have some information that we can find in our database regarding, for example, the embodied energy recycling. That is the energy that is necessary to recycle 1 kilogram of materials. This is another project that we have produced with the company that produce a plastic bottle, and we have to find an alternative material to PET. These are the constraints that we have put in our project, and our objective were minimize permeability to oxygen, minimize the cost, and minimize the embodied energy. We produce different a life cycle assessment and the impact category that we are measured were primary energy and carbon footprint. We compare the initial configuration of the bottle with a new solution with thinner walls and a third solution with a recycled content. As you can see, there is a comparison in terms of primary energy, and you can find that using thinner walls and recycled content, we have a reduction of primary energy if compared with the initial configuration. Then we go on, we create a project in order to define an alternative to the PET, and we find different alternatives. And one of the solutions that we proposed to the company, and they go on with this solution, was the application of PLA, biopolymer from lactic acid. And here you can see the results of the LCA. Last application, a comparison between among PET, PLA, aluminum can, and Tetra Pak. Also in this project, we compared the LCA of these 4 different applications. And in the last slide, you can see the histograms. And you can see that the Tetra Pak option has the lowest value in terms of energy and also in terms of CO2 footprint. So this was only a very short presentation to describe to you in which way also simulation and the correct instrument can help us in manage the plastic transition. Thanks a lot for your attention.
Thank you, Silvia. Also, to keep on time. So, I'm also glad to introduce the Materials Engineering University of Trento. Has really a long history about research and activity and project, around 40 years. And with Higgs' biggest department, like polymer, where are working around 40 people, introduce really a lot of innovation in terms of materials. So we have here Giulia Fredi and Andrea Dorigato with his presentation related to how waste can be used to increase the bio content. See, in particular, the case of most interesting, promising solution also, the wood plastic composite. Thank you, Andrea.
Thank you for your presentation, and good afternoon to everybody. Today we will talk about lignocellulosic reinforcement for composites material, polymer for reinforced plastics. We start from a lignocellulosic reinforcement, and we will focus our attention on natural fiber that could be mineral, animal, but we will focus our attention on cellulose and lignocellulose fiber, in which we can find different kind of fibers that can be obtained from bast, from seed, from lead, from stalk, from lead. So we have a huge variety of natural fibers, and you can see the worldwide production of this fiber, and as it could be expected, wood fiber has a huge production in the world. It is the most widely produced natural fiber. And in fact, we will try in this presentation to focus our attention on wood polymer reinforced plastics. Lignocellulosic fiber means practically the dry part, the dry stuff of plants. It is the 60% of the total biomass in the world. It can be obtained by wood biomass, extracted by plants, or by the crop waste. Why they are so important? Because they have important advantages with respect to traditional fibers, in particular glass fibers, in the sense that they are light, they have a low cost, they are renewable, in many cases they are recyclable, low energy consumption in the production, and in many cases they are also biodegradable. So thanks to these advantages, they could be interesting also for the material science in different fields. We have different methodologies to extract natural fiber, in particular physical, mechanical methods, the rethinking. that in Italian means macerazione. But in any case, after that we have produced, extracted this fiber, we have to compatibilize them with the polymer matrices because they are hydrophilic, and many thermoplastics are hydrophobic. Therefore, there are many thermomechanical treatments, like the silanization, according to which we can improve the compatibility between the fiber and the matrix. A bit of chemistry. What is lignocellulose? What is wood? It is composed by three components. Cellulose, that is an organic compound, and a linear polysaccharide, like it is, okay, with a very ordered structure, with a high crystallinity. Then we have hemicellulose that has the same chemical structure, but it is amorphous, with a random structure. And then we have lignin. Lignin is a cross-linking phenolic polymer that is formed by the polymerization of different primary monomers that you can see in these slides. They are the alcohols of the lignin. It is a 3D structure, very resistant, and protect the structural part of the wood, that is the cellulose. You can see that for different lignocellulosic material, you can have different percentage of lignin, cellulose, and hemicellulose. In the lignocellulosic fiber, in which you have a very high cellulose content, you have a very high strength, a very high stiffness. So the mechanical properties of these fibers are primarily due to the content of cellulose within this material. But there are other important physical features that we have to take into account. This is the typical structure of wood, hardwood, softwood. You can see that it is a very porous material that could be constituted by a multi-layer biocomposites. Each fiber has a diameter of 30, 40 micron, and a length that ranging from 1 millimeter for the hardwood, from up to 8 millimeter for the softwood. But going more into detail, you can see that we have a fiber in which we have the middle lamella consisting of lignin that connect the cell walls of this fiber. The fiber are formed by a primary wall outside, and inside we have the secondary wall that is split in 3 layers. The secondary wall is responsible of the mechanical properties of this lignocellulosic fiber. On the central part we have the lumen, that is an open channel in the center of the microfibril. Going more into detail, you can see that in the secondary wall that is responsible for the mechanical properties, we have helically arranged crystalline microfibrils of cellulose. The angle formed by these cellulose fibrils with respect to the longitudinal axis is known as the microfibrillar angle and determine the stiffness and the strength of this fiber. In particular, from this graph, you can see that increasing the fibril angle, you decrease the elastic modulus and the mechanical properties of the fiber. The result is that, if consider lignocellulosic material, we have elastic moduli that could be 20, 30, 40 gigapascal, theoretically. So the result is that wood and lignocellulosic fibers are orthotropic material, anisotropic material in which the longitudinal properties are different with respect to the transversal one. Here you can see the difference between the longitudinal and the transfer elastic modulus of different wood. The density is important in the sense that the mechanical properties increase linearly with respect to the density of the wood that we consider. And more generally, we can say that natural fiber are among the stiffness and the strongest material, the natural material that we have at our disposal. It is important, this chart, because I would like to compare wood, flax, and hemp fiber with respect to the main fiber that are more commonly used in the market, in particular e-glass and carbon fiber. If we consider tensile strength, we can consider that also in absolute term and in specific term, natural fiber cannot compete with carbon fiber, and nor also they cannot compare neither with the e-glass fiber because they have a lower tensile strength. But if you consider tensile modulus, we can see that the most important natural fiber can compete with the e-glass fiber. And they are also lighter. They are much lighter with respect to the main fibers. So this natural fiber can be an important competitor for glass fiber, not for carbon fiber. This is the most important consequences. Another important thing is obviously the economical issues. From this table, you can see that on the average cost of natural fiber is generally much lower with respect to the traditional X-glass fiber. And if we consider the eco properties, the embodied energy of natural fiber is much lower at the production with respect to the E-glass fiber. And impressive is this chart, because if you compare the carbon footprint and the price of natural fiber, you can see that it is much lower with respect to that of carbon fiber and the most advanced fiber like Kevlar and ultra-high density molecular weight polyethylene fiber. So very cheap and eco-friendly material. So now we can pass to the composite that we can make up with this lignocellulosic reinforcement. And this kind of material, natural fiber composite, can have some advantages like the low density, the interesting mechanical properties in terms of stiffness, renewable origin, potential biodegradability, recyclability in some cases, and a lower cost. But they have also some challenges, some drawback. In particular, low dimensional stability. Natural fiber can have non-reproducible physical properties, lower chemical resistance, lower environmental resistance, and a propensity to biodegradation that in some cases could be a negative issue. We can generally classify these composites as fully bio-based, in which we have both matrix and fiber that are bio-based, partially bio-based, in which we have a synthetic matrix in combination with bio-based fiber, but we can have also hybrid biocomposite mixes to different fiber types. In practically speaking, we have a very versatile class of material. We can combine different kinds of polymer matrices, both petro-based and bio-based, biodegradable and non-biodegradable, by using different kinds of reinforcement. So we can use particles, we can use flakes, we can use short fiber, we can use non-woven mats, or we can use long fiber in order to produce long fiber composites with very high mechanical properties. For the market, the natural fiber composite market has a huge increase in the last 10 years, but you can see that the greatest part of this market is covered by wood plastic composites. Here I reported the global wood plastic composites market in terms of volume and revenues. So a huge increase in the last 10 years, especially in the sector of the building and for the production of novel automotive components. The global market of wood polymer composites is formed by polyethylene, 65%, PVC, polypropylene. In the other polymer, we can have some thermosetting resins like epoxy resin or phenolic resins. The reinforcements are in form of wood fibers made up of hardwood or softwood, or you can use a wood particle that could be supplied in different range in the micron, some 100 diameter micron range. They are very versatile material in the sense that we have different processing routes to prepare these kind of composites. We can use thermoplastic material thanks to the extrusion and compounding. We can use the composites pellet to produce injection molded product or extruded profiles. Or we can produce sheets that we can use in the compression molding. In the case of the thermosetting resin, we can use the typical processing steps of composite laminate, traditional composite laminates, in particular compression molding, vacuum-assisted resin transfer molding, and pultrusion. An important issue, if you see this thermogravimetric chart, is that the maximum process temperature for this kind of composite is about 200 degrees. Okay, so we have a limiting temperature for these composites. Last slides, we have many factors that affect the physical properties of this material, in particular the kind of the matrix we select, the processing techniques, the fiber content, the fiber orientation, and the interfacial strength. It is difficult to have a general overview about the mechanical properties of this material, but you can see that in terms of strength, stiffness, all the natural fiber composites follow a linear trend. In particular, we have an increase of 10 megapascal of tensile strength if we increase of 1 gigapascal the stiffness. Obviously, that the reinforcement form has a governing effect on the mechanical properties in the sense that the unidirectional composites perform better with respect to the bidirectional of non-woven fabric composites. Thermosetting-based material are better in general with respect to thermoplastic. And these kind of composites has comparable specific properties with respect to glass fiber reinforced polymer and some non-metal alloys. Once again, these kind of composites cannot compete with the carbon fiber reinforced polymers. So the competitor is glass fiber reinforced polymers. In this chart, if we compare unidirectional thermosets and unidirectional thermoplastic reinforced with glass fiber and natural fiber, it is immediately clear that if we compare moduli, specific moduli and absolute moduli, we have a good comparison, okay? They are similar, they have similar stiffness. If we compare instead the tensile strength, the glass fiber perform better with respect to natural fiber. The conclusion is that the natural fiber can be alternative to glass fiber reinforced polymer only in stiffness critical application, but not in strength critical application. Last issue related to the cost, okay, here compare the mechanical properties and the specific cost for different kind of thermoplastic and natural fiber composites. You can see that they have a lower cost with respect to glass fiber reinforced polymers, and they have a much lower cost with respect to carbon fiber epoxy composites. And the same also if we consider the tensile modulus. So they have a very cheap alternative to this more traditional material, and they have also a lower environmental impact. If we compare, for example, an underfloor panel for automotive application, if you prepare it with a flex reinforced polypropylene instead of using glass reinforced polypropylene, you have an important non-renewable energy saving at the production. The same if you consider other kind of automotive component like this. And here I reported other example. If you replace the material with the 30% of glass fiber with the 40% of KNF fiber, you can see that you have a reduction of the greenhouse gases emission of 10–15%. So I hope that I convinced you that this material could be a good alternative for many industrial applications, but now it's time to leave the floor to my colleague Giulia Freddi that will explain and show you the challenges and industrial opportunities for this material.
Thank you very much. Giulia Freddi, still from the University of Trento, Department of Industrial Engineering. So following on from what my colleague has presented, I will focus more on the challenges and opportunities of lignocellulosic reinforcements. And no, as we have said, that the physical mechanical pros of these fibers are their low density and their high specific strength and stiffness, but they are hygroscopic, no? And they have a lower strength than most synthetic fibers. From the processing point of view, instead, they have a non-abrasive effect on tools, and they are non-harmful, no? And no skin irritation, which is good for workers, but they degrade above 200 degrees, so it's challenging, no, for the processing. From the environmental point of view, of course, they are a good alternative because they are renewable and they have they cost less than the man-made alternatives, but they show lower durability, and the quality is can be variable. So yeah, the benefits again are these, no? Cost-effective, high specific properties, lightweight, biodegradable, which is a pros and a con, and vibration damping capacity. Therefore, they are being used already, no? For several types of applications in the automotive industry, in the construction and building industry, but also in the consumer's good, in the sports good, and also in other types of transportations. My presentation will focus quickly on, especially on the challenges, no? And what we can do, no, to tackle these challenges. So, to summarize all the challenges that natural lignocellulosic fibers bring, I think that they can be divided into three main groups. The first challenge is the poor interfaces with the polymer matrices. In fact, they are hygroscopic and hydrophilic. Therefore, they have a poor interfacial interaction with polymer matrices, which are mostly more hydrophobic. But they also absorb water, and this causes swelling of the natural fibers, which further degrades the interface. The second challenge is the poor stability in general of these fibers. So they have a poorer thermal and environmental stability than other types of fibers like glass. And this has two main consequences. So they degrade during processing above 200 degrees, more or less, no? And this is challenging, especially if you want to combine them with technical thermoplastics, no? Like polyamides, polyamide 6 or polyamide 6,6, no? It is not a challenge if you want to combine them with polypropylene, of course. Also, they degrade during use. They are being attacked by fungi, microorganisms, no? And they also show higher flammability than, for example, glass fibers. The third challenge is instead associated with the property variability. In fact, they are both variable in time and from batch to batch. And it is also challenging to measure their properties because their cross-section, for example, is not constant. They are not perfectly cylindrical, for example. No? So both, and they also, so their properties varies depending, for example, on the different locations on which they are grown, on the different precipitations, the different temperatures on which they are grown. And these are not only controllable variables. Bonus challenge, the first of the two challenges actually showed a decreased durability, no, of durable composites. And maybe also for the, those composites which are intended to be biodegradable. Okay, starting back from the first challenge, the poor, so the hygroscopicity of the fibers, that the fact that they absorb a lot of water causes a stress on the interface. In fact, you can see that if the fiber absorbs water, it can swell, and some water-soluble substrates can leach from the fibers, and therefore the fibers will shrink. No? When the environment is dry again. And this, of course, decreases the interfacial strength with the polymer matrix. This occurs both with hygroscopic matrices like polyamides, but also with non-hygroscopic matrices because all the matrices present like porosity. Moreover, the single cells, the single fibers can swell due to their hygroscopic nature, and this, again, will be an anisotropic property. They will swell differently on the axial and on the radial direction, and therefore, and this will cause a further deterioration of the interface. What we can do? So we can tackle this hydrophilicity and this hygroscopicity by surface treatments. So the aim is to remove the hydrophilic hydroxyl groups from the fibers and to replace them with something else. For example, we can have chemical methods like mercerization, silane coupling, esterification, acetylation, etc. Or we can have physical treatments like plasma, ozone, corona treatment, etc. For example, two of the most important chemical treatments are the alkaline treatments, so treatment with NaOH, for example, and the acetylation, so treatment with acetic acid or acetic anhydride. And what they do is, in one case, the breakage of hydrogen bonding in the fiber structure, and in the other case, for the acetylation, instead, what we are aiming at is to bring an esterification of the hydrophilic hydroxyl groups, no? And to substitute that with something else, as you can see here. For example, here you can see the different treatments from typical palm date fibers. You can see how the morphology is changing by increasing the concentration of NaOH in the solutions. But if you use too much NaOH, what happens is that you basically fill the surface fiber with defects, and this will decrease their mechanical properties. So a little bit is okay, too much is not. The same is true for acetylation, for example. Here you can see how acetylation contributes to decrease the water absorption of these kind of fibers. But if you use too much, so the acetylation treatment is too harsh, you will eventually decrease the mechanical properties, the tensile modulus of both the fibers and also the final composite. So if you use too too little acetylation, you will end up with a poorer adhesion, so the mechanical properties will be low. If you use too much acetylation, you will degrade the mechanical properties of the fibers and the surface, and therefore you will end up with a composite with lower mechanical properties. Okay, moving up, the second challenge is instead the poor thermal stability. Again, 200 degrees is set as the maximum temperature to which we can process the natural fibers. This, of course, is a problem with, again, engineering thermoplastics, because it's not a problem with thermosetting resins and low melting temperature thermoplastics. No? But these 200 degrees maximum, or 230, 250 degrees maximum, limits strongly the processability with engineering thermoplastics. The current solutions involve chemical treatments, which offer only moderate improvements, or also coatings, like with epoxy resins are being explored as a possible solutions. But in my opinion, for example, these authors present an epoxy coating on flex fibers, and the increase in thermal resistance is only moderate. Still, this coating brings a considerable improvement in both the tensile strength on both the fibers and the final epoxy composite. So it could be a solution. Okay, another solution could be changing completely the processing of thermoplastics. No? If we substitute the traditional thermoplastic processing with a reactive processing, no? We end up working at a lower temperature, and this could be a solution not to overcome the famous 200 degrees Celsius. This can be done not with all the thermoplastics, but only, for example, with polyamide 6. Now, you can start by the monomer, by the low molecular weight and low viscosity precursors, and you can inject the monomer directly in the mold and the mold containing the fibers already, and in the presence of some initiators and some catalysts, and in total absence of water and moisture, otherwise this will not work, you can end up with a PA6 matrix composite reinforced with your natural fibers. As it can be observed, for example, from this paper. These authors could achieve a high conversion only after mercerization of the fibers, because they use a too sensitive initiator, in my opinion, but they still achieve good mechanical properties by a PA6 flex composite. Very interesting. We actually work on this topic, on reactive PA6 in our lab. The fact that the poor stability combined with the property variability is what is observed here in the slide instead, that the lignocellulosic fibers also have with them the so-called kink bands. No? The kink bands are these folds over here in which you have an increased porosity, and they, of course, massively decrease the tensile strength of the fibers and also the tensile strength of the final composite. Lastly, the property variability. We observed a variability as a function of the growing conditions. For example, this study involved several types of parameters, like the flex variety, the location, the precipitation, temperatures, the year of grow, the degree of retting, and they measured these other parameters like the flex yield, the fiber diameter, etc. And they, in fact, noticed a massive effect of the non-controllable parameters like moisture, or precipitations, or temperature during that year on properties like the diameter of the fibers and finally the tensile strength of the fibers and also, of course, the tensile strength of the composite. Yeah, my presentation is finished, so if you have any questions, I will be available at the coffee break at the end. Thank you.
Thank you so much. We are quite close to the end. And we are also close to change a little bit the perspective. So we had really interesting presentation related to the mechanical property of new biopolymers. Now we change a little bit the perspective to additional function of biopolymer, like the aesthetic one. So please tell us, next speaker so is Alex Terzariol. So he will give us a little bit some, from another perspective, as I mentioned, a little bit perspective of what can be done also with biopolymer. Thank you, Alex.
Thank you, Andrea. Okay, good afternoon. Are you tired? A little bit. Okay. I would like to present in a short time a little bit about product design, about our studio, because it's really important to connect materials, technology with products. Products, they are able to go in the market. So this is the reason why, for us, it's really important not only to understand the properties of the materials, but it's important to understand in which way we can transform this material in a good product. Just a few words about Design. We are a strategic design consultancy based here in Bolzano. In our team, we have different competence. We have designer, we have engineer, we have a strategic designer, we have data analyst and CMF specialist, color, material, and finishing. And this is the reason why, for us, a lot of innovation is starting from the materials. This is our organization. We have 2 offices in Bolzano and in Milano, thanks our head of business development, Elisabetta Ripamonti, and other offices in the world. Because for us, it's really important to understand the different behavior, the different habits of the people in different countries. And sometimes we receive from this ambassador, we name the ambassador, a lot of information about new material, new technology, and so on. This is really important because thanks to this information, we can create different products. As you can see, in different sectors. We are working in consumer industry as well in investment goods. So one important aspect is mathhub.eu. This is a material library we created many years ago in which we have not so many materials, but the most important material for our use in different sectors. There is a lot of material library in the world, of course, but in our material library, we try to connect not only the material, but the material with the suppliers, with technology, and sometimes with the possible use in different sectors, concerning with regulation, of course. Thanks to this Math Hub, to this material library, we are able to suggest to our client different materials to be innovative on the market, because this is a very important aspect in that case. Polymeric material play a fundamental role in product design, and in the last time, biopolymers are more and more important for our use. One of the most important aspects for product design is the aesthetical approach, of course. The aesthetical approach means the appearance of the material. And as we saw in the last year, one of the most important aspects is the color and the finishing. Of course, we are talking about technical performance, strength, mechanical performance, and so on. But for product design, not only that it's important, because the appearance, the perceptive quality of the product are part of the aesthetical approach. We saw that two colors are very important and very trendy in the last years, yellow and green. Yellow and green in different, of course, nuance, in different gradation, but they are very important because they communicate that we are talking about a special material. We are talking about a biopolymer. And last but not least, the finishing. The finishing has to be very soft, with soft colors, with this texture in a very soft way. This is a very important approach for the biopolymer. Today, I would like to talk about 4 different keywords relating with materials, relating with products, and relating, of course, with design. The first one is the advanced polymers. This is the next generation of PLA. We have heard a lot about all these material. I go now in the technical specification. But for us, it's important to understand in which way we can use this kind of material. One of these is made from castor beans. The name is Pebax. And thanks to this material, we designed it 15 years ago, not yesterday, 15 years ago, these Alpine ski boots. Thanks the use of this material and thanks the use of this network, as you can see, we give to this product lightness and high performance. So this is a very important aspect because we started 15 years ago with this topic. Today, all are talking about sustainability and biopolymers, but for us was a very important issue. Other kind of products are these in which we can use the transparency as a very important aesthetical approach. In that case, this kind of material could substitute the glass, the typical glass, or other kind of typical polymeric materials. Another interesting materials is Arnitel Eco. This is a very interesting copolyester thermoplastic. Delivers high performance with a very low environmental impact. What is very important is foldable. Foldable because, of course, at the end of the LCA, you can compose it in a very small dimension. Another interesting approach is the scalability of these materials. In that case, we are talking about the new performance of biopolymers because, of course, we are talking about materials. They are used in a technical way, like this water pipe, PVC free fossil. So it's a new family of material, and it's interesting because thanks to this technology, thanks to this material, in Netherlands they are using this water pipe for a long kilometers. Another interesting approach is the seaweed-based. This is another very nice material because it's used in a very different ways for packaging, for other kind of use. What is really important for this material? They don't create microplastic, or the microplastic are biodegradable. So this is another important aspect. Last but not least in this topic is this material, Ortholite, in collaboration with Novamont, created this kind of special material with sole shoe. And it's interesting because it's available for over 500 brands in the world. So this is, I think, a standard today. Another topic is the resource preservation. Of course, it's really important to preserve the resource. And in that case, by utilizing byproduct from the food industry and agricultural waste, we have an alternative biopolymer. So thanks, for example, to the waste of beer brewing, we have an interesting material, a granulate that is used in different ways. For example, in the fashion sector, thanks to this material, as you can see here, we can have a special leather. This leather have a very interesting finishing and a very interesting taste. So it's really important for different situations. Another material very interesting is this bio-based from food waste, such as banana peel or these nuts. And as you can see, we can have different products in different ways. And today, all these kind of products are part of our daily use. Last but not least, in this topic, it's almost seaweed resin. In that case, for single use, all what is single use, it's a problem today of plastic. So this is a good alternative on other materials, and I think could be, from the aesthetical point of view, a very good alternative in that way. Last topic, enhanced degradability. Of course, it's another important aspect, for sure, in which we could find different products based on bacteria. So this is the next very important topic for this product. We are talking about PHA material and without leaving harmful microplastic. So this is very important because we have to treat the argument about sustainability with coherence. Otherwise, it's difficult to have a very sustainable material, but if you don't have the traceability and if you don't have all the process under your eye, it's very difficult to give to this material or to the product the possibility to be really sustainable. Another interesting product is BioSear Flex. The name of this sandal is Balena, and this is very interesting because it's a fully compostable thermoplastic elastomer, replacing toxic fossil and fuel-based materials in consumer goods. It's interesting because you can use granulate for injection molding or extrusion. So this is another very interesting possibility to use this kind of material. The last in this topic is a polymer from plant residues in agriculture. This is another possibility we have today, thanks to this new generation of natural polymer materials. In that case, we are talking about plant residues that are using for different use like that. Not only for the single use, but for other kind of mechanical use. So just an overview about the possibility today with biopolymers, with a new aesthetical approach, with a new vision of future, because sometimes people are thinking that sustainability it's a little bit not so really attractive. No, we try to maintain this aesthetical approach. We try to transform maybe a new aesthetic to give to the products a very good appeal. I have the last point. It's a case history from our studio, just to give you the possibility to see in which way product design could transform a material. We are talking about fruit crate. You maybe have seen in a lot of situation this kind of product. We designed it for a company here in South Tyrol, Palbox. This new crate starting from HDPE, this material, but using a special technology, Muchel, is the possibility to mix the injection molding with a gas. In that case, we used less material, of course. In the old crate was about 35 kilo weight. We are here about 28, 27, 28. So in that case, the possibility to use this kind of network could give to the crate a good resistance and a good structure. You can see here the product. The product is in production today, and what we talk about with our client is to collect the old crates, to regranulate the old crates, and to create the new crates, but other material, other product too. What is the very interesting performance of HDPE? That is a typical amorph material, and the mechanical characteristics are the same after the regranulation too. So that allows us to create, for example, another different product. This is a compostable litter bin for at home, because we observed that a new behavior at home is to use compostable elements. After the pandemic, our behavior are changed, and in that case, our idea was to transform the typical compostable element in a worm station, because thanks to the worm, it's possible to transform biological waste in a special soft, and this is a fertilizing. As you can see here, different use, different situation. This compostable element is modular, as you can see, and it's possible to use in different situations, for a single use or for a family or I don't know what. It was my last slide, and I hope that it was informative for you today.
Thank you, Alex, to this change of perspective. Very interesting. So now we are close to the end. So as well, I have to thank all the speakers for their really good contribution to this event. But I have also to say very thanks so much to our NOI event organization, in primis Iris Cristelli. Thank you. And also Astrid Brunetti and Veronica Steiner, and also the in-house meeting management, Federica Levighi, and also Company Green for the good technical support. Thank you. So for the speaker, I think that we can take a picture together, and after that, we can enjoy also the buffet. Thanks so much.